Okay. So I'm going to talk about... Posso fechar aqui? Tá um pouco demais. I'm going to talk about some works I've been doing the last years at Goiânia, and mainly about the vector, light vector and axial mesons dynamics, and mainly their couplings among each other, and two constituent quarks. So this is the basic outline. There might have some small changes of the order of things. So I give the motivations and framework, and then I talk about how I reach the couplings of constituent quarks to light mesons from departing from a QCD effect, a part of the QCD effective action. And then I start by talking about this in the vacuum, and then later I will do this for weak magnetic fields, weak with respect to the quark constituent mass. And then I will talk about an unusual sort of anomalous coupling of vector mesons to the axial constituent quark current, and the axial light meson coupling to the vector constituent quark current. And then I'll show some results, numerical results or comparative results between these couplings, and then I reach some conclusions. So the motivation for that is very clear. I think it's been part of the motivation of many people. And then to reach some sort of a bridge between the QCD and the hadron world that can be measured in laboratories, I will use the constituent quark model, and which may have some limitations. I mean, it's very often to find corrections to the usual picture, standard picture of the constituent quark models, such as include diquarks and other states. And sometimes it's a little bit confusing to talk about constituent quarks because they should not be quasi-particles. Anyway, we assume they are somehow quasi-particles of the system. And then there are two main ideas about the constituent quark models. It's about when the quark is dressed by a gluon cloud, and then when a constituent quark is dressed by a pion cloud. So this approach, it merges these two possible clouds of the constituent quark. Of course, the constituent quarks also, usually the constituent quark model assumes the dynamical chiral symmetry breaking, according to which we have the large hadron masses with comparison to the quark masses. And also, of course, the aim of this conference is to discuss many effects of the strong magnetic fields. And although strong, in this case I'll talk about, they are not strong, they are weak with respect to the constituent quark masses. And of course, many things have been discussed in this conference, so I will not extend further in this part of my motivations. And then the idea is to take this part of QCD effective action from the quark sector. This is a quark-anti-quark interaction mediated by a gluon that is not a simple gluon exchange. This is a gluon that is dressed by self-interaction, so by the non-abelian dynamics. And then by considering this term, I will extract, I will bosonize somehow quark-anti-quark states to find meson fields. And it appears here also the role of this non-perturbative gluon that gives rise to the gluon cloud. We know that if we take a very large gluon effective mass, we reach the Nambu-Ionalazinho model that copes very well with the standard quark model. And then I will not talk about that, but I've seen several talks about the Nambu. I will show some results we have got about the Nambu-Ionalazinho at finite magnetic field also. So this is a starting point. we have this degenerating function with the free quarks. It's missing here the electromagnetic coupling. And then we have a quark-anti-quark interaction with a gluon exchange. So this is a gluon propagator. I will not calculate a gluon propagator. I will take this gluon propagator as an external input, and it will incorporate somehow gluon non-abelian dynamics. This sort of model has been investigated a lot during the last decades, and mainly to extract results for this meson sector. And then what I find out is this way. I just split the quark field into a background quark that will give rise to the constituent quark, and the quantum quark field that will give rise to quark-anti-quark mesons, the C quarks, and the C quarks, I mean the quark-anti-quark scalar condensate. For that, I introduce the auxiliary fields. And then with the auxiliary fields, the pion cloud appears. So from here, from the background quark, we have the gluon cloud, and then from this side of the calculation, we have the pion cloud. So if you just neglect the meson sector, if you just stick to the quark sector, we obtain this sort of interaction that is a Nambu-Lazinium type interactions, where if we consider the non-degenerate quark masses, we have flavor-dependent coupling constant. And besides being flavor-dependent coupling constant, where ij belongs to the adjoint representation, we also have a split between the scalar channel and the pseudo-scalar channel. So they behave quite differently in this Nambu-Lazinium because the quark mass, quark effective mass, is not momentum dependent, it's a constant. So the behavior of these two coupling constants, scalar to the scalar, are very different. And then we have to choose to provide with correct calculation. We choose dealing only with the scalar coupling constant. That here are these we have since they are flavor dependent, we have up, down, and strange. They are different among each other when plotted against the magnetic field. And then here, there is also a comparison with lattice results. That's results that were extracted to cope with the lattice with Nambu-Lazinium. And then there are other types of parameterizations from, this is from Andrew D. groups, and other types of parameterizations of the coupling constant dependence on the magnetic field, different ones from papers that aim to reproduce the pion, mainly the pion, neutron pion mass. And then we see that the coupling constants become quite different, only the scalar sector. In the pseudo-scalar, they go very different, going up instead of down. And then we obtain this kind of result. I will just show that. This is a lattice result. And here, I forgot to write the legends. The same labels would appear for the two usual parameterizations, yellow and red, and then our results a little bit up. In fact, it's this one here, this black thick curve. And then there are all this sort of non-degenerate behavior of the coupling constant in all channels of the interactions. So this brings some of course, this is only calculations from the Nambu-Lazinium. It considers nothing more from QCD. So it brings us the question, what is an effective model? So you take inputs from QCD, but also have the necessary results from the whole model. So this is a loop calculation. So how to deal with an effective model might have some different ways. Dash line, this is the calculation with a pseudo-scalar coupling constant. The other one that goes well up to this magnetic field, this is the scalar coupling constant. We would expect to work with the pseudo-scalar, but it doesn't work with the pseudo-scalar coupling constant. So this is the starting point. This is the quark determinant with a vector of the meson sectors. Here I included 3 of them, the vector axial mesons, the pion or pseudoscalar and scalar sector, and the quark currents that are already addressed by the gluon cloud. I will not talk about the possible renormalization of the meson sector. This is done somehow for a different model, for the Yukawa model, when we also do a very similar calculation by focusing in the renormalization scheme for this sort of calculation. So I assume when needed, the renormalization is possible, even for the effective model, but most of the couplings I will talk about are finite, ultraviolet finite. Yes, they don't have ultraviolet divergences. And this is a sort of benchmark of the calculation. This is an effective field theory that Weinberg proposed 10 years ago, 12 years ago, that coupled the constituent quark with the large NC procedure. And then we obtained this effective field theory only considering the pion sector and the constituent quark sector. So we have here the terms from chiral perturbation theory and background gluon, and then the coupling of the background gluon pions to the constituent quark. So this was a sort of benchmark to verify that our method provides good results. And then I did also that for under a weak magnetic field. When you do that, I started by considering a background photon, and then this calculation provides the correct electromagnetic coupling of photons to constituent quarks and photons to pions. So this comes from in this covariant derivative, and then we have here the terms from chiral perturbation theory with the electromagnetic coupling. Also, besides that, I have computed the symmetry breaking terms with electromagnetic coupling, also from chiral perturbation theory, besides those couplings of quarks to constituent quarks to pions. So this is a sort of benchmark of the method. Now, for the vector meson sector, these are the couplings, the leading couplings of the vector and axial mesons to the vector current, constituent quark vector current, and axial current. So there is an ambiguity of dealing with the Fermi determinant. So here I show the results in which the vector meson coupling is different from the axial vector to the axial current, or axial meson coupling to the axial current. So, but if we impose unitarity or emiticity of the operators, we have equal couplings of the vector mesons to the equal to the axial couplings. These couplings correspond to these diagrams, where here we have the constituent quark with this gluon cloud, and the leading vector and axial meson are these ones that I take from the PDG. So this is in the vacuum. When you include, when you go one step further to take the next leading terms, we have an anomalous coupling of the vector, light vector meson to the axial quark, constituent quark. And here, this is isotriplet coupling, the rho coupling, and this is the omega coupling to the axial current. This is a triangle diagram, and they have these couplings have the structure of a Veso-Minovitine term, which we can include on extra dimension to show that these whole couplings might be quantized somehow. It's not clear if they are quantized in the current, in the quark current, or the whole, or if the vector meson select a sector of the axial current to be quantized. And then when you go to, this is a comparison between the axial, the pion axial coupling to constituent quarks with this anomalous vector meson coupling to the axial constituent quark current. So this coupling constant It is dimensional, it has dimensional energy to -2, and makes it to be reduced strongly with respect to the pion axial coupling, but they keep the same momentum dependence. Here there's a comparison of this coupling constant with the light vector meson coupling to the consistent quark at some energy scale that are the quark and light vector meson momentum of the order of the constituent quark mass. This goes 10% of this vector meson coupling. And then to verify the effects of a weak magnetic field, I consider two mechanisms. The first one is by means of the photon coupling to the charged mesons and constituent quarks, and also, of course, this is the main mechanism, the effect on the internal lines, quark internal lines. But they lead to the same terms with a different numerical factor. And then when considering the first method, the first result is the electromagnetic coupling of the vector mesons and the charged vector mesons and charged quarks, and that comes correctly by means of the appropriate flavor and Dirac structures. So these are the couplings of an axial light meson, axial meson to the constituent quarks with the pseudo-scalar current, and then the vector meson with a scalar current. And then all these coupling constants, G1, and here there is the limit of wake magnetic field, and this photon field correspond to the wake magnetic field configuration. These coupling constants are always written as integrals of the quark propagator and of the gluon propagator as well. And yeah, so the electromagnetic coupling appears correctly. Here we have higher order couplings of the photon to the system, to the quark currents and the light vector meson and axial meson couplings. These couplings are reduced by 1 over m squared or 1 over m star. That's the constituent quark mass. So this expansion is good for large quark mass. It's a large quark mass expansion. So if you go close to the chiral symmetry restoration transition, of course, it looks like that would not be valid, but at the same time, the running coupling constant would also decrease, so there might have some, depending on how these quantities decrease, the expansion might still be valid. So when you include the weak magnetic field effect, we have quite asymmetric couplings between this is the vector meson, light vector meson rho tensor, the XY components, and then here the omega tensor, this is stress tensor, this is the isotriplet axial stress tensor, and this is the singlet axial tensor. They are coupled to the scalar and pseudo-scalar currents in the leading order. And they are very asymmetric. They lie basically in the plane perpendicular to the magnetic field. And then we have direct estimates of their order of magnitude among themselves and with respect to the coupling constants in the vacuum. So typically, they are proportional, the ratio of the corrections due to the magnetic field over the values in the vacuum is of the order of B over n star square. That's correct according to the expansion we have done. And then these coupling constants, in fact, they are not just coupling constants. They correspond to the zero momentum limit of form factors. So with this, we can extract also average quadratic radii for the light mesons. This is an example of the rho average quadratic radius that is extracting this usual way, with its contribution in the vacuum and its contribution due to the magnetic field. So this is the value of the average quadratic radius. With respect to the magnetic field, it decreases considerably. So here we have the two curves in the vacuum, stars in the vacuum plus the magnetic field correction. So the shape of the rho should be a little bit oblate. So we can also compute magnetic field corrections to the anomalous coupling. It keeps a very similar form of the coupling in the vacuum. And here we have EB over m star square. This is the leading correction with the momentum dependence of the isotriplet rho coupling to the axial isotriplet current. And this is also the isotriplet rho coupling to the axial current. They are strongly momentum dependent. And here, the strict magnetic field correction, it also leads to strong asymmetry that lies in the plane perpendicular to the magnetic field. And also there is here a term that are included in the strict mesonic coupling of the vector meson to the axial, light axial meson. That's a kind of mixing between both. That's only possible in the presence of a third particle or in the medium, because otherwise it would not conserve momenta. I mean, this Levi-Civita tensor, it requires particles to be perpendicular to each other. So to conserve momentum, there must have someone else close to be able to do that. But there is here a vector meson mixing to the axial meson. And also there are other couplings to the pion and so on. This is an example of a form factor dependence on the momentum. This is the vector meson momentum. And here for different consistent quark momentums and effective masses. So just to show some order of magnitude, this axial coupling of the light vector meson provides us with an estimate of a correction, an axial average quadratic radius of the light vector meson, the rho, which is of the order of 1/10 of the rho average quadratic radius calculated with the same method. And then the magnetic field correction to the axial radius of the rho is 1/10 of this small quantity. So the last thing I would like to talk about is about the strict vector meson sector. And then there is a mixing between the neutron rho meson to the omega rho meson that has been studied since the 60s years by many people. It has some role in several reactions, and then I extract some estimation for this mixing and its correction due to the weak magnetic field. So when expanding this vector meson sector, free terms, we have some terms that break gauge symmetry because of the way the expansion has been done. So this can be corrected by a redefinition of the photon and the vector meson fields that restore gauge invariance and kills the photon mass that would come from these terms. This was proposed by these people, and then we can do that systematically in this level of the quark determinant. And then we extract effective couplings for the vector meson dominance. This means a photon that becomes the neutral rho meson or the omega meson. And we have the correct relative strength of their coupling constants. So we also have the photon coupling to these mixing terms or these vector coupling, vector couplings. This is a three-leg diagrams. sometimes with a photon that induces the vector meson mixing, rho and the omega, and the light mesons couplings, and a photon that corrects the vector meson dominance. This is a omega coupling to the photon with an external further photon. Curiously, it does not go to zero. It remains because of the polarizations, the possible polarizations of the photon and the vector mesons. And then this coupling here corrects the vector meson dominance. And then one of the tests I did, I calculated the pion form factor as a function of momentum by including the photon coupling, the photon correction to the vector meson dominance, and the photon coupling to the vector meson mixing. And in fact, this is the pion factor, the pion form factor that measured in this reaction, this annihilation reaction. So here there is no magnetic field, but there is this further coupling of the background photon to this, both the vector meson dominance and the meson mixing. So there is a slight improvement in this time-like region. So when I go to the magnetic field, terms, we have here strong, also again, strong anisotropies that make this vector meson dominance and meson mixings to behave a little bit different than usual. So these are my final remarks. I think the method is quite reliable. It comes from an important term of the quark effective action from QCD. And it yields several aspects of low energy phenomenology, and it's very useful or suitable to calculating medium corrections and systematically temperature, weak magnetic, strong or weak magnetic fields, and the temperature, and then this is a part of what I intend to do in the future. Okay.
Thank you for the talk. Usually in a Wood-Jones elastine, when you work with finite density or study the rho meson, you have to include the vector interaction, and nobody knows which the coupling is. Usually, it's people guess what it is, some fraction of proportional to the scalar interaction. Do you have some estimation of which this radio of GB, GS could be?
Yeah, I have some estimation, a very preliminary estimation. And in fact, when you do this calculation, the vector sector, the correction to the vector coupling constant is different from the correction of the scalar and pseudoscalar. They are all different. Each channel has a different correction. And then it would be different, but I mean, they lie all around 20 to 30% of the original coupling constant.
But
without the initial vector coupling, without that, I didn't take that. I only took the standard Nambu-Jones Lagrangian, and the result of this calculation is that all these couplings, after the calculation, become different. The scalar, pseudoscalar, vector, and axial may be different.
But the difference between them, between the scalar and the compared with them, this is about 30%.
No. The 20 to 30% is the difference with respect to the original coupling constant. Okay. Among them, it depends on the channel because they also, all of them will depend on the flavor. If you consider non-degenerate quark masses.
Yeah. Okay. Thanks.
Thank you, Fabio. I didn't quite get how you did the systematic expansion for low magnetic fields. Can you just briefly synthesize that information?
Yeah, well, first of all, there is this large quark mass expansion in this determinant, and then for the weak magnetic field, there are two ways. This is the most used way. This is should be the more important contribution, that the quark propagator, you can expand the quark propagator for weak magnetic field. This is a standard expression. If you go to Schwinger-Popper's-time, you get this kind of expression in the leading order. And then here, there is also, I let the freedom of the background photon to correspond to a magnetic field correction, to a magnetic field configuration. I mean, if the magnetic field is so strong, you might have photons with virtual photons, but in a large, with a large occupation number. I mean, I do some sort of hypothesis in this sense that the photons will represent the strength of the magnetic field. But, and in fact, the result, they have the same shape. They have a small difference in the numerical factors, the coefficients. But they contribute equally.
More questions? If not, let's thank, yeah?
No, here we only calculated the Schwinger phase. I neglected the Schwinger phase. There was a reason for that, but maybe I should remind first. I neglect the Schwinger phase. This is just the, maybe I will have some reason. I have to think a little bit more to remind it. Okay.
Let's thank Fabio again.